There are, however, a great deal of numbers that cannot be factored easily or really at all. Numbers like 2, 3, 5, 7, 11, 13, and so on, where the only pieces that we can possibly break that into are the number themselves and 1. The free multiplication, the free factors that every number gets just based on how we define that operation in arithmetic, where we call numbers such as this prime numbers being ones whose only factors are 1 and the number as they're written, where the study of prime numbers dates back to work done by the Egyptians, but the exact notation that we have calling them prime specifically comes from the work of the ancient Greek mathematician Euclid in his opus, as it were, the Elements, where what he said was, excusing my inability to pronounce Greek, protos arithmos esten homenadi mone metromenos, which is most often translated as a prime number is that which is measured by a unit alone, where in this case the word prime comes from the Greek word protos, and so it means first. And also the word they used measured, or at least the word that gets translated to measured, probably today means something a bit closer to divides. So we can say that the primes are in some sense the first numbers, the numbers that you cannot divide any further than they are written, and can thus be used to make other numbers in terms of multiplication, where the numbers that can be divided in that way, the numbers that do have more than 2 factors, more than the trivial guaranteed factors, are called the composite numbers, where we do say that for the composites we're looking at numbers greater than 1, and that sort of throws 1 into a gray area, because 1 kind of doesn't have the 2 factors you want for it to be prime, but it's also not really composite. In this book, we avoided that by making them greater than 1, so it's all kosher and 1 exists on its own. But in some contexts, you'll see people argue that 1 should be considered a prime, and others argue that it shouldn't. I personally fall into the camp that it's its own thing, but you'll probably be able to find cases that could argue either of those ideas fairly convincingly. Anyway, though, we're not going to be too worried about that special case as much as we're going to be worried about another idea of Euclid's, which is the idea called the fundamental theorem of arithmetic, which also comes from Elements, where he said that up to arrangement, every composite number could be represented uniquely in terms of its prime factorization, in terms of the primes that when you multiply them together, you get the composite, where we can visualize that using a thing called a factor tree, and that's what we're going to get an example of next. So for this example, we want to find the prime factorization of 700, where for this, again, I could write it all out, but it's a little bit easier to picture that using that tree diagram I talked about. What we're going to do is we're going to take the value 700 and we're going to split that up into parts. What parts we pick are kind of up to interpretation. There's nothing that says we have to start with a certain value, but for me, the most obvious one to pull out there is 7. As I talked about earlier, 7's not a nice number to deal with, so we're just going to get it out of the way first. We're going to pull that out there and think of 700 as being 7 hundreds, so 7 times 100. That 7's a prime, so we're stuck with that. And then at the 100, we can split that a few different ways. I'm going to go with 2 times 50 here. You could also do 5 times 20 if you prefer, but we'll do 2 50s. And then we're going to have a 2 and a 50. 2's a prime, so we're good there. Then at the 50, we can split that into 2 and 25. Again, it's up to your choice, but that works for us. 2 is still a prime. 2 is the only even prime, to be sure. So then we have 25, which is 2 5s, and as a whole, that's what our prime factorization could be visualized as. So if we want to actually write it out, the way we usually do this is in ascending order for the factors with each power to condense it down. So we'd end up writing this as would be 700 is equal to 2 raised to the second power, 2 squared, because we have 2 2's in that factorization, multiplied by 5 squared, because we have 2 5s in that factorization, and then multiplied by 7, because even though it's the first one we found, it's our biggest single piece, and we only have one of those. Or one thing to mention with these prime values is that there's evidence to believe that primes go on and on forever and ever and ever, just like the rest of the natural numbers do, but we don't actually have a solid proof, a solid argument that says they have to, or that they have a finite ending point. And in particular, for those of you who are interested, or those of you who would like to know more about this, the most recently discovered largest prime was found in 2018 by Patrick LaRoche of Ocala, Florida, so fairly local, and has almost 25 million digits when represented in base 10, so quite a large number. And there's evidence to believe it will keep going beyond that, although we haven't found the next biggest one, where in particular the Electronic Frontier Foundation, in accordance, in conjunction with other organizations, is offering a prize of $250,000 for the first person to discover and show the validity of a prime number that has over 1 billion digits in base 10. We're still a little bit away from that, but hey, if you're looking to make a chunk of change, could be a fun problem. Anyway, that's what we have for primes and factorizations. The next things we're going to be looking at are how we can use those in terms of greatest common divisors and least common multiples.